Hello, I am James Walden, a professor at the Center for Information Security at Northern Kentucky University. In this presentation, I'm going to explain the impact of a major security event on an open source project, in particular the impact of the Heartbleed vulnerability on OpenSSL. We'll start by looking at OpenSSL and Heartbleed and why they're important, and then we'll look at the evolution of vulnerabilities through the history of the project. Then we'll look at our methods for analyzing time series of monthly software and project activity metrics before we come to our conclusion. So OpenSSL is a free open source software library that provides both cryptographic algorithms like AES, Diffie-Hellman, and so forth, as well as an implementation of transport layer security, which at the time that OpenSSL was created was known as SSL. The project began in 1998, and as of the year of Heartbleed, was used widely in both servers and clients, including well over 1 billion Android devices and about half of the Alexa top million websites and almost half the top 100. So the Heartbleed vulnerability had about the biggest press of any vulnerability up until that time period, perhaps in part because it had a cool logo, but more importantly, because it affected such a large percentage of both clients and servers on the internet. And the vulnerability was exploited. There were data stolen, including bitcoins. The country of Canada delayed its tax filing date due to Heartbleed. And so it had a wide range of effects. And of course, everyone had to replace their TLS certificates because of it. And in fact, as a result, it used a substantial percentage of internet bandwidth and cost major providers like content delivery networks millions of dollars just for expiring their old certificates and replacing them. So our goals for this project were to see how the open source community responded to Heartbleed and how the project itself changed in response, both in terms of processes and policies, security vulnerabilities, project activity, and software quality metrics. And then we want to see what we can learn from this incident in terms of how to evaluate and improve open source software. So there were two community responses, replacement or repairing. So the replacement projects resulted in two forks of OpenSSL, one by Google. Android now uses their own boring SSL, which still takes a lot of code from OpenSSL. And the OpenBSD project created its own library, LibreSSL. On the repairment side, the Linux Foundation created the Core Infrastructure Initiative, which provides funding for projects to improve their security, and they created a badge program to assess the security of open source projects. The project itself responded in 2014 by publication of a security policy, but we don't really see an effect in terms of the code or policies yet. What we had initially was the hiring of full-time developers. Before Heartbleed, the project had no paid developers and subsisted on about $2,000 in donations, which is incredibly small for a project used by billions of devices and that much of the internet depended on for its security. The big code changes started in 2015 when the project created a coding style, reformatted the whole coding base to follow that style, removed old features like SSL version 2 and support for certain older operating systems. And finally, they also finally specified end-of-life dates, which was important because as of 2015, version 0.9.8 had been out there and being updated for 10 years. In 2016, the project reassessed itself using the Core Infrastructure Initiative's badge and scored a passing score of 102 compared to its 62 as of the time of Heartbleed. They started fuzz testing and performing static analysis on a regular basis. And they released their first new major version, 1.1.0. This removed a lot of old code and is actually the only major release of OpenSSL that was smaller than its predecessors. In 2018, a second major new release, 1.1.1, came out supporting the TLS 1.3 protocol, as well as new cryptographic algorithms like SHA-3. This version did resume growth. So the number of vulnerabilities reported per year increased dramatically with Heartbleed, as we can see from the huge spike in the graph starting in 2014 and going through 2016. In fact, over half of all vulnerabilities in the project's 21-year history were reported in just those 3 years. And this indicates that really the number of vulnerabilities that a project currently has really doesn't tell you much about the number of undiscovered vulnerabilities that may remain in a project. So a fairly inactive project, as OpenSSL was in 2014, may show a relatively small number of vulnerabilities compared to what actually exists in the source code. So for analyzing our activity and code metrics, we're going to use a regression discontinuity design. This is a quasi-experimental approach to evaluate the causal effect of an intervention, in our case, the Heartbleed vulnerability, and the project's responses to Heartbleed. And the idea is that we can observe the intervention based on how the time series changes afterwards, with the idea that it would have remained the same without the intervention. How do we determine the date for the intervention? Well, certainly knowledge of events like Heartbleed and responses to Heartbleed as documented in the project's mailing list and so forth can help. But also a visual inspection of the time series is another important way to identify it. And note that we want to include an equal number of data points before and after the cutoff. In my analysis, we're using monthly metrics computed with the first check-in into the Git repository at the beginning of the month. Our equation for RDD is a linear regression equation. We've got a function d that represents the discontinuity, which is 0 before the cutoff date and 1 after the cutoff date. So this means that the regression coefficient tau indicates the change in the mean of the metric after the cutoff, and the coefficient beta 2 indicates the change in slope after the cutoff, whereas alpha is the level before the cutoff and beta 1 is the slope before the cutoff. So for developer activity metrics, we choose the Heartbleed date as the cutoff because changes began immediately after Heartbleed. We start seeing a substantial number of increased commits and increased authors. In fact, 95% of all authors contributed only after Heartbleed. Many of those authors are single commit authors because the number of commits before Heartbleed and after Heartbleed is about the same, although note that there's only 5 years after Heartbleed and there were 15 years before Heartbleed. The size of OpenSSL changed and it decreased immediately after our cutoff date in this graph. And note that our cutoff date in this graph is not the Heartbleed date, but rather it is the date when major code work began in February 2015. And this date's identified by both looking at the graphs and looking at the mailing lists and blog entries and so forth that the project had published. Now, Layman's sixth law of software states that software tends to increase in features and size. And this shows that the response to a security incident may be the opposite of that. A project may decrease in size to improve security. And OpenSSL is doing this largely by removing entire files. As we can see, the decreases in files and statements follow the same pattern. However, while the number of functions decreases immediately after Heartbleed, note that the slope increases substantially after Heartbleed. So to explain why this is happening, I looked at the average function length and saw that it was decreasing after Heartbleed with a fairly strong negative slope. So this means that the project members are refactoring OpenSSL to have more smaller functions, which is probably a good indicator of improving code quality. Another indicator of code quality is nesting depth. It's difficult to read code that's deeply nested. And before our cutoff date in February 2015, the maximum nesting depth was 13. After that date, it decreased to 7. And this decrease affected almost 100 files with max nesting depths over 7. The mean nesting depth only increases by about half a level at the same time, largely just because these very large nesting depth constructs were replaced. We also see that traditional complexity metrics, including cyclomatic and Halstead complexity, both decreased after the code reformatting and changing in 2015, and they continued decreasing. They've got a negative slope in both the complexity metrics. Finally, one of the biggest reasons for the changes in 2015 were to make the coding style of OpenSSL consistent with their newly published code style guide. This metric is computed by QMCalc based on 19 measures of various code formatting things, such as is the brace on the same line or on the following line after a while statement. And a number of 60 is actually quite high. I examined a variety of open source projects, and a lot of them average below 10. But we see they did a tremendous improvement. It dropped from about 60 to about 4 in February 2015. Now I wanted to look a little further out beyond the regression discontinuity analysis of the 2-year period before and after the cutoff. So I looked at style inconsistency through the end of 2019. And we do see that it starts increasing. And this is to be expected. There's not a constant reformatting out there. But even though it is increasing, it's still tremendously lower than it was before Heartbleed. We also looked at language features, and one of a particular one was the use of the C preprocessor for conditional compilation. OpenSSL supported a lot of older operating system and used a lot of complex and nested if-def statements, which can make the code hard to read. And we see that actually that was also decreased during this big change in 2015, and that the use of C preprocessor conditionals continued to slowly decrease afterwards. So this is an area of continual improvement. So what was the impact of Heartbleed on OpenSSL overall? So there's a dramatic increase in the number of vulnerabilities reported for 3 years. And this is a good thing. So that shows a lot of vulnerabilities are being identified and remediated. And the average level has returned to fairly normal pre-Heartbleed levels as of 2017. We saw a tremendous increase in project activity, with more than half of all the commits happening after Heartbleed. And not just from the newly employed full-time developers, but we saw a lot of contributions from single commit authors. And the project may be more inviting to those because of the improved coding style and so forth. Code size decreased significantly after Heartbleed in the run-up to the release of 1.1.0, but it resumed growing as new features were added with the 1.1.1 branch. Code complexity decreased significantly in 2015 and remained at historically low levels. Style inconsistency decreased even more, but it started to grow slowly, although it still remains within fairly normal values for an open source project. And finally, use of conditional compilation used via if-def decreased significantly and continued to decrease or remain at a low level. Finally, as for the repair versus replace argument, clearly repair is one. OpenSSL remains the most widely used TLS library in public servers. I did an analysis using the census.io IPv4 search engine, and LibreSSL made up less than 0.01% of servers. Boring SSL is used primarily on clients and is, of course, dominant in the Android space, while OpenSSL is still widely used in IoT devices. So what are our takeaways from this? One, security incidents combined with resources can dramatically improve an open source project. And in fact, that project activity and practices, as perhaps measured through the CII badge, may be better indicators of security than simply counting the number of vulnerability reports. Finally, the OpenSSL dataset for this paper, along with the code used to produce the models, figures, and tables in the paper, is publicly available at the URL on this slide. The paper itself is available as a preprint. So thank you, and I look forward to seeing you in the live session and getting your questions there.